Bismillahirrahmanirrahim. Hello everyone. So hopefully you all will be fine. So in today's video, I am going to discuss the types of armature winding. Okay. Last time in last tutorial, I discussed construction of DC generator where I discuss all the principal components. So in that principal component, one was the armature winding. Okay. So in that tutorial, I discuss in detail about the armature winding. So if you did not watch that video and if you want to watch that video, then you can click on the my channel name, Engineering World by Naveed. Then after that, you go to the playlist where you will find electrical machine playlist. So in electrical machine playlist, you will find all the videos related to electrical machine. Okay, so in today's video I am going to discuss the wave winding and lap winding. Okay, so first come toward the wave winding. So in wave winding, basically we have two parallel paths. Okay, so if you want to construct electrical machine and you construct electrical machine and now you are going to do winding. Okay, you are going to do armature winding. So you will do it depend on the demand. Okay, if demand is high voltage, like if you want to generate high voltage from the electrical machine, then you will do wave winding. Okay, and if you want to generate high currents, then you will do lap winding. So wave winding, we have two parallel paths. Okay, so this is the figure of wave winding. So in wave winding we have two parallel paths. Okay, and all the coils are connected in series. Okay, this coil is connected in series with this coil. So EMF generated in this coil will be add up to this EMF plus this EMF plus this EMF, and in this way we get a one EMF that is equal to the EMF of one parallel path, and you will get that EMF as a EMF generated. Okay, so you will get that EMF over here because this EMF is equal to this parallel path and this EMF is equal to this parallel path. Okay, this is the brushes. Okay, this is positive sign. Okay, so current will flow outward from this brush, and this is negative sign, so current will flow into the brushes. Okay, and let's say I have Z number of conductor. Okay, total number of conductor is Z, then Z by 2 conductor will come in these slots. Okay, and Z by 2 conductor will come here. Okay, so let's say we have 24 number of conductor. So 24 divided by 2 is equal to 12. So 12 coils will come over here and 12 coils will come over here. Okay, now let's come toward the current. So if here the current is IA, then here the current will be IA by 2, and here the current will be IA by 2, and the current direction will be into the brushes. Okay, so here the current will flow like this, and it will flow in the load resistance. Okay, now let's draw the wave winding. Okay, so wave winding is basically like this. It is basically like this. Okay, it will be in the form of wave shape. Okay, so this is my back pitch, this is my front pitch, this distance is my commutator pitch. Okay, because this is the here, from here we give connection to the commutator, and from here we give connection to the commutator. So the distance between these two commutator slots is your commutator pitch. Okay, so this is your average pitch. Okay, so in wave winding, your average pitch will be equal to addition of back pitch plus front pitch divided by 2. And one thing that you must remember in wave winding, and that is your back pitch and your front pitch must be an odd number. Okay, it must be an odd number, while the average pitch can be an odd number or it can be an even number. Okay, so you must remember these two things, because in most of the MCQs, in most of the entry tests, these MCQs come that if your back pitch and front pitch will be an odd number, it can be it will be even number, or it will be both even or odd. So you must remember these two. Okay, it must be an odd number, and this average pitch can be an even number or odd number. If let's say my back pitch is 5 and my front pitch is 3, then if you add these two, 5 plus 3 is equal to 8, 8 divided by 2 is equal to 4, which is an equal even number. Okay, but if your back pitch is equal to 7 and your front pitch is equal to 3, okay, then your average pitch will be equal to 7 plus 3 divided by 2, so it will be equal to 10 divided by 2, which is equal to 5, and that is an odd number. Okay, so you basically your average pitch can be an odd number or it can be an even number, but your back pitch and front pitch must be an odd number. Okay, so your average pitch can be equal to Z, which is the total number of conductors, plus minus 2m divided by P. So M is basically equal to 1 for simplex winding. It means that one winding in one slot. And M is equal to 2 for duplex winding. It means that M in one slot we have two winding, two parallel paths. Okay. So plus is used for progressive winding and minus is used for retrogressive winding. Acha, one thing which you must remember in wave winding, we will not use an equalizer ring. Okay, why we will not use an equalizer ring, that I will discuss later on in lap winding. Okay, so now let's move toward the lap winding. Okay, so your lap winding in lap winding is a bit different from the wave winding. So in lap winding we have total number of p parallel path, where p is the number of poles. So it means that your lap winding depend on the number of poles. So in if let's say we have 4 poles, okay, we have 4 poles, so total number of parallel paths will be equal to 4. Okay, so here I draw the parallel path. So and this lap winding, as I already discussed, that this lap winding is used for generating high current. Okay, how high current? Let's say last time I took this, that if Z is equal to 24, so there I get 12 coils per parallel path, but here I will get 6 coils per parallel path. So here I will be having only 6 coils. Okay, so here if one coil generate only 1 volt, so 12 coils will generate 12 volt. Okay, so that is high voltage, 12 volt. But here one coil generate 1 volt, so here one parallel path will generate 6 volt. Okay, so that is less than 12 volt. So it is used for the high current, for generating high current, and wave winding is used for generating high voltage. Z by P is the number of winding in one parallel path. Okay, if this is a armature current, then in one parallel path there will be IA by P armature current. Okay, so your EMF generated, that will be equal to EMF, okay, per parallel path. Okay, so you will get that EMF generated over here, because all these connections are in parallel, so EMF will be same. And your current is equal to P, which is number of poles, times current per parallel path. So here the current in one parallel path is IA by P. So if you put that IA by P over here, then times P, so you will get IA. Okay, now let's come toward the lap winding, that how you will do lap winding. Okay, so it will be something like this. Okay, it will be like this, then it will like this, then it will be. So in lap winding, one coil, okay, let's say this is first coil. This first coil will superimpose on the second coil. Okay, but in wave winding there is no superimposition. Okay, this is first coil. First coil will not superimpose on the second coil. Okay, and second coil will not superimpose on the first coil. But here, this is my first coil, but second coil superimpose on the first coil. Okay, okay, so now let's move, let's come toward the pitch. So this is my front pitch and this will be my back pitch. So the pitch of the winding is equal to YB minus YF, and average pitch will be same as in the we discussed in the wave winding, that will be equal to YB plus YF divided by 2, and your commutator pitch will have a constant value that is equal to plus minus 1. Okay, there is in lap winding we have the number of brushes will always be equal to the number of poles. But one question which come in your mind is that here I have four parallel paths. There are four poles, but I use two brushes. So this is just for your understanding. I draw only two brushes, but actually here four brushes will come. Okay. So if I also draw the other brushes, so then the diagram will get complicated. So that's why for simplicity, I use only two brushes and connected all parallel paths to these two brushes. Okay. Okay. So now let's come toward the equalizer ring. So equalizer ring is used for the circulating current. Okay. So here, as I already discussed that equalizer ring will not be used in wave winding, but it will be used in lap winding. Okay. Let's say I have three batteries and voltage rating of each battery is 2 volt. Okay. So this 2 volt, these 2 volt, and these 2 volt. Let's say this is battery A, this is battery B, and this is battery C. This is IC, IA, and IA and IB, IC. Okay, so all these batteries will generate equal current. Okay, and that's current I will get over here, and that current is equal to IA plus IB plus IC. So that's current will flow over here. But here I will get 2 volt because of the parallel connection. Okay, 2 volt I will get on here, and current will be greater than each current. That will be equal to IA plus IB plus IC. Okay, let's suppose battery B generate 1 volt. Okay, let's say there is some sort of error come in the B battery, and it is unable to generate 2 volt. Now it's generating only 1 volt. So there will be some sort of current flowing in this direction as well. Battery C will also supply current to battery B, and battery A will also supply current to battery B. Okay, just to equalize the voltage rating. Okay, so this will sacrifice his current, and this will also sacrifice his current, and in this way all these three batteries will keep a one voltage because of the parallel connection. So then there will be some sort of circulating current flowing over here. Okay, there will be some sort of circulating current flowing over here, and and here you will get less than 2 volt. Okay, so similarly in generator we have yoke. What is yoke? I discussed this in last tutorial. And we have core connection. So yoke and let's say yoke and core connection of one winding is not equal to the yoke and core connection of second winding. Okay, let's say there is the connection is not too much perfect. Okay, let's say this connection is little bit loose. So because of this, your EMF in one pole will not be equal to the generation of EMF in the second pole. Or you can say that due to the dust or due to the impurities, dust on one coil will not be same as the dust on the second coil, second pole coils. Okay, so that's will due to dust, that's there will also be some sort of different EMF generation in two poles. If you see over here in wave winding, this winding cover all the poles. Okay, this cover all the poles, and this will also cover all the poles. Okay, so all poles will get covered. Okay, this also cover all poles, and this also cover all poles. Or if yoke and core connection of one pole is not the same as the yoke and core connection of the second pole, then then difference will come over here, and same difference will also come over here, because this this winding, these coils cover all the poles, and similarly these coil also cover all the poles. So any changes come in this in here, any changes come over here will have the same changes come over here. Okay, so if there is a decrease in EMF over here, then the same decrease will of EMF will come over here. Okay, so but here in lap winding, as I already discussed that in lap winding, there is one coil superimposed on the second coil, and second coil will superimpose on the third coil. Second coil superimpose on the first coil, and third coil will superimpose on the second coil. So that's why here in one pole we have number of windings, then in second pole we have number of windings, then third pole we have number of windings, and fourth pole we have number of windings. Okay, so four parallel path will come over here. Okay, so four parallel path. Let's say here the dust is too much. Okay, so EMF will generate, so less EMF will generate over here, and here the dust is not too much, so that's why high EMF will generate over here. So there is a difference in the EMF. Okay, so between two parallel path there is a difference in the EMF. Or you can say that, let's say this, the yoke and core connection of this pole is too much tight, while the yoke and pole connection of this is not too much tight. So that's why the generation of EMH will be different from each other. So due to this, different current will generate. Okay, here the current will be I1, and let's say here the current is I2. So if you give this connection directly to bridge and this connection directly to bridge, so if this current I1 incident on I2, so due to unequal current, it will be short circuit over here, and it will generate a spark, and because of the spark heat will generate, and because of the heat your brushes will get destroyed. Okay, so what we will do, so for this we will use equalizer ring, okay, which is a copper ring. Okay, so it will short circuit all the parallel paths. Okay, so and here we give one connection to the bridge, so the bridge will receive a uniform current over here, and same we do use equalizer ring over here. Actually, there is one last thing which I want to discuss, and that is your EMF is equal to NP pi Z by 60A. N is the speed which is calculated in revolution per minute. Okay, revolution per minute. P is the number of poles, phi is the flux, and this is the number of conductors. Okay, 60A. So your A will be equal to 2 for wave winding. Okay, if using wave winding, so you will use A is equal to 2 over here. Okay, but if you are using lap winding, then for lap winding, your A will be equal to P, and P is the number of poles. Okay, so this is all about the types of armature winding. So if you have any question related to this video, you can post it that question in the comment box. Or if you want to suggest any topics which is not clear to you, so I will try my best to make a video on that specific topics. Okay, and thanks for watching. Allah Hafiz.